All right, so I'm going to start with just asking for some volunteers first. So I have some things I'm looking for, so if I have to guide you to it, I will, but I think maybe you found a couple to get started with. Any volunteers first? Yeah, Luke?
Heat energy in a match.
Heat, okay.
And the chemicals that pick up the match.
Okay, so, okay, heat energy is in the match chemicals. I'm going to say chemical bonds, though. Just got to expand upon that because it's not just chemicals, the bonds in the chemicals. Okay? Will? Something else?
Most spontaneous chemical reactions are exothermic.
Okay, so usually spontaneous reactions are exothermic. Good. Raise your hand. Mandika?
A reaction that absorbs heat is an endothermic.
Good. So we all should know that absorbing heat, so I'm just going to label heat as Q, is an endothermic reaction. Good. I'm going to put a little plus by that to remember. Marissa?
Heat is the result of bonds being formed as a substance crystallized.
Okay, so sometimes, actually most of the time in crystallization, that was the last example, right?
Mm-hmm.
So in the crystallization process, it says it like super cool. So it took a seed crystal and it crystallized. So it's in solution, it's kind of fluid, and it crystallizes. So technically, we're going from liquid phase to solid phase. And you said this was endo or exo, Marissa?
Is it endo?
No, you just told me. What'd you say?
Oh, I didn't say it. I said
You said heat was.
crystal. I said being formed as a crystallized.
So heat was being formed as it crystallized. So heat was being formed, meaning it was released as a product as it was crystallized. So I think everybody can tell me if heat's released, it's what? Exo, okay? So as this is crystallizing from liquid to solid, heat is released, right? Which we then would call exo. And we kind of knew that because we knew from liquid to solid this was medium kinetic energy, and this is small or low kinetic energy. So that has to be an exo process. You have to release that heat. And who's ever had one of those hand warmers that when you pop the little disc in there, it crystallizes? You guys know what I'm talking about? That's warm. Like it feels warm. If you don't, I have one in the back. I just have to melt it again. But those are recyclable. You can keep reusing them. Give me a couple more. All right. I can get volunteers or I can ask for you guys. Let me get somebody who's not helping me out here. Grant, what you got?
Ammonium nitrate causing cold fracture.
Okay, so yeah, ammonium nitrate is one of the only things that we use to make a cold pack, to make an ice pack. Other than ice, right? So that's one of the fun facts you maybe didn't know, but that's a good review of ammonium nitrate, right? Izzy, you got something?
Nothing that's not already. I wrote it down the compounds that get cold whenever they dissolve in water.
Okay, so for this particular example, it was a solution process. So basically the solid ammonium nitrate dissolved in water and it made it cold. Okay, what you got, Jacob?
That's a long one.
Okay, let's get some more. How about, what did it say about bonds? Did it say that whenever you made a bond, it released energy or absorbed energy?
Oh, to break
So-
bonds.
All right, so to break a bond, heat must be absorbed. So to make a bond, heat must be released. Okay, so to break bonds versus to make bonds or form bonds. This is an important fact we should know, okay? So breaking bonds, you guys said, uses up energy, so is that endo or exo? Endo, because it's going to absorb energy. And then to make or to form bonds, it's going to be exo, so it's going to release energy. Okay, do me a quick favor. I want you guys, I'm sure you've seen the TV show Ice Cream from Disney. Oh gosh, it's old. It's like 70s. Okay, so put your arms like this. So Audrey, she would twitch her nose, and she'd do this, and then like that, and she'd make her twitch through. All right, come on, you guys have never seen this?
No.
Okay, well anyway, I see your arms like this. Okay, so I want the person next to you. So one person's gonna keep their arms crossed, one person's gonna keep their hand like this. Okay, so Cam's gonna be my person. All right, so I am going to break this bond. Okay, so I'm going to break up this bond. Break it open. I said it really hard. Boom! Oh, she broke open. Okay, so did I put energy into this, or did I take energy out of that? I went into the bond, right? So I broke it, and then he broke the bond. Okay, and then as he kind of comes back and calms down, I'm just gonna. release energy, right? So release that stress, Cam. Just release it. Oh, thank you. Okay, so to break a bond is karate chop, and so come back together and kind of, whew, you're going to release that energy, and that's what these two are representing. Okay, that's a pretty good list, guys. Anything else you want to add? All right, so just remember, there are chemical processes and solution-based processes that can cause a heat to be exchanged. So the solution process and the crystallization process, were these chemical reactions, crystallization and solution? No, none of those reacted. They didn't form new things. They just made a solution or they made a crystal. Those are not like new substances though. So the one that talked about rusting, like the iron, what did it say? It said iron, you shook it and what happened?
The faster it rusted,
The more heat, right? So it actually, it's like a porous barrier. So when you shake it, the iron filings and the oxygen air react and they combust. It's not catching on fire, but it's synthesizing, probably to make iron 3 oxide and heat. And that heat we feel as a hand warmer. Those are the ones that you shake, you know what I'm talking about?
Yeah.
The hand warmers, like the orange packs. Okay. All right, so we're going to pick up from where we left off yesterday. We're going to solve an equation with our foldable, okay? Before I forget, do 2 things. Pass up the reading, because you did not write in the reading, and separate stack, pass up PS14. Pass up reading, pass up PS14.
Oh, mine is on
People can try and make 2 separate stacks, please. Do you have my stapler? All right, and last call. I'm done. Taking that now. I'm not stealing it. All right, any more readings? Any more readings?
What is this? PS14.
We're done with this. Come on. All right, PS14, hold the stack up so I can just swipe it. Thank you.
Oh, that's so.
All right, let's do this. Now, listen up, okay? So after we get the hang of like each style of question, we're going to start on PS17. So the goal is so we can practice in class, get it, and then we'll practice our homework, okay? So this is the section you wrote on which side of the foldable? Bottom left. Bottom left. So I'm not drawing my picture again, but it's like we're down here.
Now we're at the top.
Okay, no, we're not. We're right here. Okay, so you wrote all this down yesterday. We said the equation was Q equals Q, meaning we had to identify the surroundings in the system and so forth. So let's do a question related to this. We'll do this section in a second. We're not quite there yet. Okay, so we did that one yesterday. I don't think you guys wrote this down. This is the sea of water. Write this down someplace. The specific heat capacity of water. It's one we use very often, so it's one that I would like for you to know. 4.186 joules per gram degree Celsius. So because the relationship between joules and calories, you with me, Grant? What you need? All right, you get your life together, okay? All right, so this is the energy unit of joules that we'll use most frequently. Do remember, though, that 1 calorie is equal to 4.186 joules. So those 2 things are interchangeable for water. Also the sea of water. It's just you won't see the calorie option nearly as often as joules. Yeah.
So 1 calorie / is equal to 4.186.
So yeah, 1 calorie per gram degree Celsius is actually equal to 4.186 joules per gram degree Celsius. These 2 things are equivalent, and they're both representing the sea of water, or the specific heat capacity of water.
Calorie equals.
Little c calorie, the real calorie. Okay. So, and this brown is kind of hard to see, so I'll tell you what this says. What's really interesting, and we did talk about specific heat yesterday through our little video. We saw water was really high. It's like a 4 joules per gram degree Celsius. Where like aluminum is like a 0.9, copper's a 0.38, iron's a 0.45, mercury's a 0.14. So what do you notice about all these metals? Super low. So do they change temperature fast or slow? Super fast. So like you can touch a cookie sheet within minutes of it being out of the oven. But I'm not going to touch boiling water within minutes of it boiling. It's still going to be smoking hot, okay? So metals are really low, but water is surprisingly high. So that's kind of the contrasting nature we see here. All right, so that's just something we're going to use in a minute. We're going to now solve this question. So while I'm thinking about it, I do have your lecture notes. We may not do all of these, which is okay, but I want to make sure you have options, especially if you're maybe trying to run a new week and trying to come to tutoring or something. You know, how to make your practice today. It varies every week, but usually if you just ask me, I'm going to know. So make sure you grab one for Zane, okay? So please make sure those get passed back. Okay, so we're on number 1 of the second section. So it says calorimetry practice. If I didn't pass back enough, let me know, okay?
Wait, this is
Yeah.
Is that for us? Okay.
So this is,
One second. All right, so I was trying to wait until everybody got one, but let me go ahead and hold this up now. Notice I printed a couple things for you. I printed the lecture practice. Everybody looking here with me? We already did number 1 on the very top section yesterday. We're doing number 1 on the calorimetry section, and then so forth. We're going to do some more. So notice I actually printed out PS 17 for you, so no worries. And then on the back, I have a review and then some other notes that we'll be taking. So I did try to keep that all together on one. Were there any extras? Extras past 30. All right, here we go. All right, so if you would like to write this on your foldable, if there's space, you can. If not, keep this organized on a separate sheet of paper with your other notes.
so this is the.
This is the calorimetry. Yep, Q system equals Q surrounding. So it's the lower left corner example. All right, so calorimetry is the word that's going to be very, we're going to see that word, we're going to think Q system equals Q surroundings, because it's talking about transferring energy between two systems. So here we go. We have to label these very, very carefully. Okay, oops, dang it, I didn't want that one. Okay, so as I read this, I see what's the specific heat capacity? 50 grams of metal that raises 100 milliliters of water in a calorimeter, which is the cup, from 34 degrees Celsius to 36 degrees Celsius. The initial temperature of the metal is 95. The final temperature of the water in the middle is 36. Okay, so I'm hearing a whole lot of numbers, but I'm going to recognize which is the system and which is the surroundings. So what do you think the surroundings are, guys? Well, identify the surroundings. Is it water or is it metal?
Water.
Probably water. Okay, so make a little t-shirt like this and just put water. So then who's the system? Metal. And you guys have a picture of this. You drew your little picture with your cup, with your metal in it and your water. Like you can see that this is system and this is surroundings. Okay, so we want to label each individual variable for each system and surrounding. So it's asking for C, specific heat, of the metal, right? So I'm going to put C question mark. But what's the next thing I know about the metal? 50 grams, right? So what is that about the metal? What variable? M for mass. 50 grams, okay? And then it tells me water, milliliters, right? Well, what do I know about the milliliters of water and how that relates to grams of water? Say again? You guys know the density of water? One what? So the density of water is 1 gram per centimeter cubed. What we know that centimeters cubed are the same as milliliter, right? So if I have milliliters, then immediately I know that's the same number, but I'm just going to write grams next to that now. So because I notice I don't have volume in my cubic end cap, so I'm not going to put volume at all. So really, how many grams is that? 100 grams of water, okay? So put mass, 100 grams of water. Okay, so I'm just kind of categorizing this under metal and water. What's happening to the water? It's going from what to what?
34 to 36.
Okay, so 34 to 36. So my delta T, do I do T initial minus T final or T final minus T initial?
Final minus one.
Right, so you're going to do T final minus T initial to get the change in T. Okay, so we're doing 30 what? So T final 36 minus 34. Okay, so that is 2 degrees Celsius. And that's 2.0 because we do keep the sig figs as we go.
Do we have to show our work W?
So sometimes I think it's helpful because if you forget to do finalize initially, you might not get a negative if you're supposed to do a negative, so it might just force you to think about it that way. Okay? So no, but it helps. Okay, so the initial temperature of the metal was 95. What was the final temperature of the metal? 36, right? So how do I get delta T over here? 36 degrees minus 95, and now what do we get? Calculators? Grant has them back there. He'll pass them out if we need one. Negative 59. And that negative is important, so we do need to keep that very clear. Okay, what are we missing on our chart? C of what? Well, C of metal's our question. We have to solve for that. What are we missing? C of water. Guys, what's C of water? You just wrote this down.
Just 4.186.
Joules per gram degree Celsius. Okay, so essentially we have everything we need except for C. So what we're going to do here, and this is very organized, it helps you a little bit better if you stay organized. So raise your hand if you need a calculator. All right, those are the only two. Grant, you got these people? Thank you. So this is where we do Q of, now what did you guys say the system was again?
The metal.
The metal? Okay, we're going to put Q metal equals Q of who? Water, right? So we know that the heat that the metal lost or gained is equal to the water's heat lost or gained. So before we move on, can you guys tell me if the metal lost or gained energy? How do you know it lost? Change in temperature went down, right? It decreased in temperature. So this one lost energy where the water gained energy. So I'm going to use that lost and gain mentality and write it as a plus and negative now. So what do I want to write on the metal here? Positive or negative Q? Negative Q, and then the water will have gained energy, so we'll put a positive there. Okay, now I'm not really going to solve for Q. I'm going to actually plug in MCAT and MCAT for each of these Q's, because that's all the data I have for here. So Q equals MCAT, right? So I'm going to put the negative like I have, and just put MC delta T. And I'm going to put just a little M on the outside to say I'm representing the metal. So all I did was plug in MCAT for Q. Set that equal to the other MCAT, but not MCAT of metal, MCAT of who? Water. And now, so if I don't put the plus, it's understood it's there, but I'll put it there just so we're clear. Okay. All right. So which of these variables, MC delta T, MC delta T, which one am I solving for? C of the metal, right? So I need to isolate it by doing what? Dividing by.
Math.
What do I do with this negative?
Negative math.
I need to take it with me. I'm going to divide by negative math. Negative M delta T of the metal on both sides. Now I'm showing all this rearrangement. I'm showing my work. When you get to the place where you can solve classes that you can, but this is just very, very clear on what I'm doing. So this negative cancels, this M cancels, this T cancels, and that gives me the C by itself, right? So that's what that is what I'm looking for according to my question over here. So I'm going to plug in all this junk over here to solve for C. So let's do that together. So C of metal is equal to all that right there. So MC delta T for water. So what's the M for water? 100. 100, right? Grams. What's the C of water? All right, somebody other than Jasmine, thanks, darling. Joules per gram degree Celsius. What's the T for water, everybody else? 2. Okay, so our table's really organized. It helps us really stay clear on what we're talking about. 2 degrees Celsius. All of that divided by, okay, so we did check, check, check. Divided by what? Negative 50 grams, so that's our 50 grams of metal. And negative 59, right? So what happens to these negatives? They cancel each other out. They will like kind of negate each other to make a positive. And that will always happen. We will never have a negative answer for a specific heat capacity. All right, so before I take questions, I want you to work with the person next to you, make sure that you have plugged this in your calculator correctly, cancel your units. What was the answer?
Yeah. So you so if we set it up
What did you do with the you're supposed to divide it by it's just the unit.
It was a small number, it was like they can calculate.
Wait, see,
Joules per gram.
I did it like so we had the top and then I had the bottom and then I tried that and then like what did you get?
All right, and back with me. What's our answer? Say it out loud. 3, 2, 1.
0.2.
Okay, so I got all this. I heard this. What units remain? Let's talk about that. What cancels first?
Grams.
Top and bottom grams and Celsius, and we're left with
Joules per gram.
Okay, so we got all this. Now, how many sig figs do I need?
3.
I think this is going to be limiting us 2 right here. So then this is 0.28 joules per gram degree Celsius. Woo! And is that a good value for a specific heat of a metal? Yes, it's low. They lose heat very quickly. Yes, yes, yes. Okay, so now I know this is a lot because you're like, oh, there's so much. Like, show your initials. Give me your equation and write it out. But if you try to take a shortcut, you might mess up something. So I think it's worth it to help streamline the process. If you find a shorter way and you're comfortable with it, I am fine with that. But I do think that first we're gonna start off with this. Okay, so let's do one more like this, and then we'll move on to the last type of equation for today. Can I move on? Okay, so this is for you. I just want to point out one difference here. I have given you calories per gram degree Celsius. Works the same way as joules, though. It's just a form of energy.
They're going to keep it.
They're the same. Yeah, you can keep it in calories.
1 calorie is equal to
1 calorie is equal to 4.18 joules, but you can just write this 1 calorie. All right,
Oh.
here. Figure it out. Let's go.
We can just write it 1 pound.
No.
I think it's like I can just feel like okay, let's say still stopping it.
I have no
Follow the same process we just did. Make a chart. No, you guys work together. Make a chart just like we did.
Like 4.18.
Yes, you take 32, 30, yeah. Final,
Well, eventually we're gonna have to house the jewels.
I don't know how to
What is that again? It's initial
Oh, it's water.
Yeah.
All right, give me a thumbs up if you got your data set organized, or you found another way to organize. Okay, just a clarification. Where did I get this number from for water?
The formula.
I told you the two versions of C for water. If you don't remember that 4.184 or 4.18 joules is equal to 1 calorie, you can convert. But if you can just remember 1 calorie is the specific heat of water as well, that's fine. All right, so you're solving for what here? Mass of the metal, right? So we have MCAT of metal equals MCAT of water. Who's the negative version? Who lost energy? Metal. Okay, so that's going to put the negative in front of the metal version. So divide everything here by what? To isolate the M of metal. Negative cap. Okay, so I'm going to divide by negative C delta T, negative C delta T. But this is for the metal. So that's why over here it cancels the C, the negative, and the T, leaving us M to solve for. So we're going to plug in all that junk. Okay. So mass of water, 100 grams. C of water, 1 calorie per gram degree Celsius. What was the T of water? 6 degrees Celsius. So just making sure that you plug that in correctly as final. We need the 32 minus the initial 26. And then what am I filling in the denominator? So I just did check, check, check. Got those. Negative 0.0329 cals per gram degree Celsius. Good. So you're making sure you guys got this is negative, right? So negative 55.6. Is that what you said?
Yeah.
Okay. So that delta T, 55.8. And what happens to our negatives here? They cancel. What's up? You good? Okay. So what cancels unit-wise? Everything but grams, hopefully, right? Let's double check that. So grams here and here can cancel. Calories top and bottom can cancel. Degrees Celsius, degrees Celsius, degrees Celsius, degrees Celsius. So what's weird is that this grams right now is on the bottom, but when you copy dot flop it, the grams are on top, right? So when you multiply by reciprocal, grams are on top, which is why we end up with grams. Austin, what'd you get? You guys calculate, okay? Say again?
326.83.
Can I get a confirmation?
Same thing.
So I think what did it say? It was at 100 point. Yeah, okay. So the limitation here is our temperature, because we subtract, you count that 1 decimal, so that's only 268. So then, yeah, we would round up to 330. Okay. All right, so we did MCAT, just straight MCAT yesterday. Was that with, was that transferring energy? Remember how you'd write the scenario in the foldable? Was the MCAT one transferring energy? Yay or nay? You wrote this in your foldable. Don't look at me. Look at your foldable.
Yes.
Okay, so internal heat, change, calculating heat when heat is not being transferred. No, I'm talking about just MCAT. Just MCAT. Okay, so now this is situation, this is when heat is being transferred. And that's from object 1 to object 2, from system to surroundings or vice versa. Okay? All right, so let's fill in the last, well, one of the last ones. The upper right-hand side, we're going to do the upper right. Can I go past this? Let me stay here for just a second. Yeah. Here? So, because I told you guys the equivalency for the C of water is it's 1 calorie per gram degree Celsius or 4.18 joules per gram degree Celsius. So these are two equivalent. So since this was in calories and I didn't want to have to convert to joules, I just used this version of it here. Okay? All right, so we're going to go back to our filling out our foldable. All right, this goes on the top right. Yes, top right. Okay, so this is when we're talking about a phase change, like in the crystallization. Marissa's going through that, yeah. So when we crystallized that hot pack and the liquid went to solid, that was a phase change, but energy was still exchanged with the environment. The only thing is that in the process itself, we don't say the temperature itself is changing within that process. It can release energy, but we're not saying the temperature is changing. So it's weird, but we'll see this on a graph in a second. So just make sure you note that this is a not temperature changing situation. So the one that we'll use a lot right now is Q is equal to moles times delta H. And that's because our delta H's, what does fusion refer to again? Melting. Thank you, we just went over this yesterday. Okay. So this is talking about melting, which is going from what to what? Solid to liquid. Okay. And then what's VAP refer to? Evaporization, which is liquid to gas. Okay. So what we have been referring to these previously, we've been referring to them as the energy per amount, which is kilojoules per mole. So notice that delta H is in kilojoules per mole. So a lot of times I'll reference water as our main example just because it's so familiar. So write down these two variables for water. The H of fusion for water, I'm going to approximate this a little bit, but it's 6.01 kilojoules per mole. That's the delta H fuzz for water, okay? And the delta H vap for water is like 44.01. Don't quote me on that. They're really close, but we're going to use those for now, okay? So, solid to liquid. Oh, evaporation, so liquid gas. Okay. So, what do you guys notice first of all about those two numbers? 0.01. Okay, sorry, I was thinking. They're both in kilojoules per mole. What do you notice about the main difference?
One's bigger, one's little.
Okay, so one's much larger. It's not just like a little bit bigger. It's a bunch larger. So why do you guys think the evaporation process requires so much more energy than the melting process? Raise your hand for me. Raise your hand. Help me out here. Will.
Like from a solid to a liquid, the particles won't spread out that much.
Right.
Like it's the gas that's spread out.
Right. So you're here versus like here. So you have to do a lot more work to get those intermolecular forces broken up. Okay. So occasionally, if we're given the information for this, which we will be on our test, is we'll do Q is equal to mass times delta H of fusion, or delta H like I have here. I just put delta H there. But if I have this, it's because I have grams, and I can plug in kilojoules per gram here. Grams will cancel and still give me energy. So we're going to calculate this now, okay? So I think we're down to P of phase change, which is the bottom. Okay, so it's the bottom of the lecture notes, the lowest left-hand side.
What would the picture be?
I'm going to draw one shortly, okay? Okay, so is this the first question? Yeah, okay. So you guys remember this guy, right? What's this called? Heat curve, thank you, heat curve. So we have the opportunity to see phase changes again. And what I'm looking at in this question, what phase change is occurring here?
Vaporization.
Vaporization, right? So we're going from what to what?
Solid to gas.
Vaporization.
Liquid to gas.
Liquid to gas, right? So which piece of this graph represents that? D to E, right? So this is liquid and this is gas. So if you would like to sketch this picture as your illustration, I'm going to model it from here first, and then we're going to make this, we're going to use this a little bit more, okay? So we're basically figuring out just this energy right here. So when we read this question, how many grams of water at 100 degrees Celsius? Well, why are we at 100 right now? Because that is water's boiling point, right? So this is 100 degrees right here. So that's just, helping to tell you you're at the boiling point, which is why we're understanding the phase changes occurring at this instance. Which this one, we don't really care about this. That's really not that important. We know it's got to be the boiling point if it's vaporizing, right? So this is just nonsense information. We don't really need it. I'm not going to write it down as my variables because I don't want you to think that you have to have pressure at all in terms of thermochemistry equations. All right, so how many grams of water, blah, 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 could be vaporized by the addition of 180 kilojoules? What variable is this? What variable is kilojoules? Well, energy for us we're talking about right now is what? Say again? Q, thank you. This is heat, guys. This is heat. Okay. It says kilojoules of heat, so I think you could have figured that out. All right, so the question is mass. It's given us Q, and it's telling us that it's vaporizing. So what equation only has those three things in it? Beautiful, right? And this is water, and I told you the vaporization of water, right? So technically I know delta H vap, which is like, what, 44.01 kilojoules per mole. Okay, so we know this, we're looking for M. Now, this is moles, right? So once I solve for moles, what am I going to have to do to get back here? Molar mass of water, and just call it a day. Okay, so let's go ahead and solve this one. So write out for your equation, Q is equal to moles times delta H. I'm solving for mole, right? So what do I have to do? Mathematically, what do I need to do to rearrange? Right, these are multiplied to each other, right? Does everybody understand that the opposite of multiplication is division? Okay, you lost me there. I was like, what's going on? No one's answering me here. Okay, so I'm dividing by delta H on both sides. Delta H cancels. All right, now you plug your data in. We're solving for moles, right? So what am I plugging in? 180 kilojoules divided by this number here, yes, so 44.01 kilojoules per mole. Okay, so what units cancel? Kilojoules. And then when you multiply by the inverse or copy dot flop, the moles come back up to the top. So calculate that for me. What's 180 divided by 44.01? I heard you. Hold on. 1 second, Jasmine. Let me finish this before I take questions. I'm just going to move this right here so I can work with this. Okay, so you guys said this was what?
4.08.
And that's moles of water, because the moles come back up to the top. And I need to now get to mass, because the question was grams. So what's my next step here?
1 mole.
1 mole on the bottom. What's the molar mass of water? Approximate it for me.
18.02.
18.02. Yep. Okay. And calculate. So,
73.5216.
I'm gonna go to 2 sig figs, so 74 it is grams of water. Because there's 2 sig figs here. All right, take a minute and go back and look at that question, talk to the person next to you, and I'm gonna take some questions before I move on to the next example. This is on the number 1 on the lowest part of your paper sheet.
I just want to see like why we lost out. Yeah, why we lost out.
It's just it's like an extra piece of information to say, hey, I'm at my boiling point. Well, you're probably at your boiling point if you're vaporizing, right? So it's just not important information for the problem solving process. So I don't want you to even look at it. It's not important for the problem solving process. Okay.
Wait, can you just talk for a minute?
All right, guys, do number 3 under the same section. We just were. Do number 3. Doing number 3 under the same section you're on right now.
Okay, so like, I'm good on the left side. Just be honest. What is all this stuff? Yeah, on the right side. So I was just pulling the data out of it. Yeah, and then it's a conversation. Okay, so about you, that's 18. At 40. Yeah.
I don't know.
Got
20 grams. I need to get the 3.
44 minutes. The equation when you want is
Focus, guys.
so it's Q of 8 is 4. So then we can plug our 7.
How many grams of
It says it was melting, and then that's the other piece of information. All right, give me a thumbs up if you understand how you're approaching this question. All right, some of us are already done with the question, so I'm going to quietly solve this up here, but if you're not ready, don't look at it, okay? All right, so eyes back up here. 3, 2, 1. If you're in the middle of problem solving, I think you got it then. So it said ice, but we know ice is basically just water, so we're going to melt the ice. It did say melting, so you had to think back to what was our delta H diffusion? Kilojoules per mole, right? So we took our kilojoules, Q equals moles times delta H diffusion. So heat divided by delta H diffusion is 2.25 kilojoules divided by the heat of fusion given in your notes that you just wrote in your foldable. And that gave us our moles. Then what was the last step you had to do? Change it to grams again with stoichiometry. Okay, so I just want to make sure I did like 1 or 2 examples for each of those. So there's one like concluding one that pulls together Hugo's impact and this mole fusion one, okay? So that is number, let's do number 4 under the section you're on right now, okay? Yes, we have to, because there's one on your problem set and you're not going to know how to do it, okay? Can I go past this? I need to start it with you, though. I'm going to start it with you, okay? Is this number 4?
No.
Yes, yes it is. Okay. This is number 4.
That's number 4.
Alright, guys, I need you to be quiet for me, okay? I'll wait for you guys. Okay, so in reading this question, it seems a little different. Okay, so it's giving a mass, okay? It's telling us we're changing temperature. So you absolutely have to draw a heat curve for this question. So go ahead and draw a heat curve. And I want you you to label the temperature changes. And you'll understand about what I'm talking about, because this is water, right? So we know where all of the phases for water. We know when they change to liquid into gas. We are actually getting ready to. So it says it's starting at what temperature? Negative 15, right? Negative 15 degrees Celsius. So my lowest point on my heat curve is going to be negative 15 degrees Celsius. All right, but track it as we go. What's eventually going to happen to this ice as it heats up? At what temperature does it become liquid? It's water, right? So it definitely melts, aka, or freezes, depending on the direction, but it's going to freeze here at 0. Note the 0, okay? And then what's going to happen here from B to C? It's going to melt, right? So that's our delta H diffusion we're going to be thinking about there. Okay, and then it's going to be liquid, it's going to be liquid, and it's going to be liquid, it's going to be liquid, and it's like, oh, no, I'm going to gas. At what temperature? 100, right? So this is what, I just put 2. Oh. We're putting 100 degrees Celsius here. Okay. And then what's going to happen? Okay, well, what's happening here? It's delta H vac, right? So it's definitely undergoing a phase change. And then all the way up here, it's going to be going to what? So what temperature do I stop at for this one? Yeah, so I know this is not to scale, but this is going to be my 230 here. Okay, so I've got to deal with each of these transitions individually, okay? So listen before we proceed to the calculation side. Is temperature changing here? Yes. Which equation has a change to temperature in it? Of the foldable we've done so far? MCAT, right? That's it. So I have to use Q equals MCAT to solve for the heat associated with this small change. Notice this whole question is just like saying like how much heat is required to do all of these changes. So we have to have 1, 2, 3, 4, 5 changes happening. Okay. So what equation is going to apply here where there's no temperature change? Q is equal to moles times delta H, in this case, fusion, right? I'm going to call this Q1, call this Q2, so I can kind of just keep them organized in my work. Okay, so what equation applies here? Again, MCAT, right? Because we have a temperature change. We have a delta T. So that's MC delta T. How do I calculate Q here? Moles times delta H VAP, right? Because it's vaporizing. And then lastly, what Q applies here? Yet again, temperature is changing, so we're going to do MCAT.
What is Q2
So this is Q equals MCAT. All the slants are Q equals MCAT. So Q equals MCAT, Q equals MCAT, Q equals MCAT. The two flatliners are the phase changes. They're both moles times delta H of fusion, or moles of delta H of vaporization. All right, so just for a moment, does this make sense on how we're going to be calculating the heat? So it's a big, huge process. We're taking 52 grams, 52.9 grams of ice, and we're going to send it through its solid phase. We're going to melt it. Through its liquid phase, we're going to evaporate it, and then we're going to turn it to like really, really hot gas. So there's a lot of different phase changes, and there's some other like heating elements we're talking about. So there are 5 different Qs we're going to calculate for that whole entire process. All right, who understands like how I've approached it so far? You good? Okay, so I got like 90% of us. Okay. So the M is going to be 52.9, right? I'm going to give you guys, no, I'm going to keep it like this right now. How am I going to get to moles of this? Just convert that to moles, okay? The thing that's weird is the C value changes of liquid water to gaseous water to solid water. So you know where you wrote down your C of water earlier? Go back to that and put L next to that so you know it's liquid. And then I want you guys to write down these for ice and for steam. These are all the C's of water. They're special to their phase change, or to their phase of matter. So put C of ice, 2.05 joules per gram degree Celsius. C of steam, or steam of gaseous water, 2.02 joules per gram degree Celsius. And you already have your liquid one. Okay, so we have all those. All right, so what I want you to do is, according to the setup I just gave you, I want you guys to calculate the total Q. So I can't find a Q1, Q2, 3, 4, and 5. Okay, work with the person next to you.
Yeah.
I'm gonna go back to that other side in just a second. Yeah. Yes, I'll give you all the constants because those are too much to try to keep in your head. Yeah. I'm gonna go right back to this for a second. Okay. Can I go away from the slide?
No.
Oh, okay. Like what?
Alright, yeah.
No.
Okay, so on the curve itself, A
Alright, yeah.
is all All right, try to. I want you to get Q1, 2, 3, 4, and 5. Go. Let's go. And I got you.
Final minus
No. So what did you say about Oh, so that's not the one that's I was right. In like
Let's get started on the first one. Let me actually start. Okay. All right, guys, listen up real fast. Okay, I just had a good question. Now we mapped this out so we could find our delta T's graphically. So what is the delta T from for the solid phase here? 15. So 0 minus a minus 15 is 15, right? So this is 15 degrees Celsius. This one doesn't have a temperature change, so we're good to go. What's this temperature change? Yes, so for Q3, the delta T is 100 degrees Celsius because it's going from 100 minus 0. And then what's the last temperature change? 130 degrees Celsius. So you have everything you need for M, C, and delta T. M is the mass, 52.9. C is the ice, which was it? Was it 2.05 joules per gram degree Celsius? And you have delta T. Plug and go. You have each piece you need. Let's go.
I don't know where to take it.
I think you do. You can even take your pencil up. Right? It was in cat.
So if I need to
What do you mean?
I don't know where to start.
We've been finding
Like
like
that's
that.
what I understand this.
We've been doing
So what we're gonna say is gonna be like calculate Q1. Then we're gonna calculate
So look at Q1.
What we have mass. This is solid, right? So it's ice. You see, that That's what's in capital. So that's okay. Totally got it. Do you guys want me to explain?
I'm trying to.
How long can you go out?
once I get these right. And not yet. Which ones am I on and now? Because I want to have joules and kilojoules and they don't match. So I want to change them all. And then, or you can change them all to joules, but it doesn't.
And then
I'm up here. Give me. I'm trying to solve it. No, just to have it on the board together so you guys can see it. I know what? You need to take your grams
I don't even know
and
where
just
to
convert
go.
to moles of water. That's it. Just do one straight count, straight step. Or joules. One or the other.
Oh my goodness. Can you scroll up a little
Give
bit?
me just 1 second. Okay, guys, you have pushed through, and we're gonna talk in like 30 seconds.
Oh my god. So
Oh, it's that 36.
All right, darlings, eyes up here, okay? 3, 2, 1, eyes up. Hush. Okay. Who understands the process? Okay, the process, like, once you draw your graph is going to hold your hand the entire way. You can put your hands down, okay? So unless you draw your graph, I don't think it's not feasible to keep it all in your head. Draw your graph and mark each point so you know what you have to do. So you knew that you were heating up the solid, so we took our C of solid, we got to joules, and I went to kilojoules because I ended up having kilojoules later on, so I just went ahead and put them all in kilojoules. I'm going to add them up at the end. So the second was the melting phase, so you're using the delta H fuzz, you get your kilojoules. What did I have to do here, though?
Convert grams to moles.
Right, so I just kind of showed my work up here to the side to my 52.9 grams divided by its molar mass to get moles, so I could just kind of use that for the other one later on. And then you went to your liquid, and the liquid was heating up 100 degrees, so we use our C of liquid and the delta T of liquid. We get our joules convert to kilojoules.
wait,
Yes, ma'am.
delta H fusion is where did you?
This one?
Yeah.
We used it on the melting, right here, the melting side of things.
So like where's that number?
You wrote it down on your bubble. Yep, it's constant.
So at the end you add it up and that's your answer.
Yep, and then we did our delta H vaporization, and then we did our final gas heating up by 130 degrees, but its specific heat capacity is a little different. Once we get all of these, we add them up and we get our answer. I'm just not gonna do that right now.
I got joules, not kilojoules.
That's fine. What's your, do you have a final?
184,751.
Okay. Takes a lot of energy. Alright, I need to tell you one more small thing that might make this different, okay? Yeah. Shh. Guys, listen. If the question, instead of saying I went from a negative 15 to 230, if it's instead said the ice melts from or goes from negative 15 to 35, how would your graph look? Okay, so tell me what's going on first. Negative 15 to 35 degrees Celsius. So negative 15 is down here. We stop at 0 because that's always where water is going to phase change or melt for us, right? And then we're going to go where? Up how much? To 35, right? We're not going up to 100 because it never made it to 100. So how many Q's are here? 3. 1, 2, 3. Just make sure you read the questions so you draw your graph appropriately and then you're good to go. Huh? No. There's not very many like this, okay? Okay, so here's what I want from you. Let's decide on how many lecture tables we really need to do here. Okay, I said we, I meant me. I'm sorry, I didn't mean to also. Okay, so what I want from you,
184.62 around
I want,
there.
so on the very first section where it says just let you know it's practice, I want you to do number 2, but I want you to know what are you missing right now from the problem that you need from me now? No, that's the question. I'm not going to tell you the answer to the question. You need C, okay? So here is the C of iron. Write this down for you. You ready? C of iron, 0.45 joules per gram degree Celsius. 0.45 joules per gram degree Celsius. So you're doing number 2 under that first section. You should be circling this on your lectures. Okay? And then you're going to do number...
Wait, it's 45.
It's not, it says 0.45 joules per gram degree Celsius. And then I want you guys to get some problems done on your problem set. Okay, so the problem set next door? You see it? Okay. So I want you to get some done on your problem set. Note that your problem set's not due tomorrow because we're not done practicing. So you need to go ahead and practice on your own. That is your homework. Look on the board. This is an angry statement. Get your email sent ASAP.